Hello, Honors Chemistry, and welcome to Chapter 11, Principles of Kinetic Molecular Theory. So some of this should be a review, right? The concept of gases and kind of what they look like at the particle level, and we just layer on a lot of math. So lots of fun. And it's a very common sense chapter, right? A lot of these things are things where you kind of already know things to be true, and we're just going to further define those things. So anyway, kinetic molecular theory, you do need to memorize these principles because these are going to be the foundation for pretty much every qualitative answer that you provide about gas behavior. So make sure you know them and you can explain them. So one, it says that particles are in constant straight line motion, right? Meaning that they constantly move, kind of like a tennis ball would, right? It will go straight, straight, straight until it hits something, at which point the energy will then be transferred, and then it will keep moving until it bounces off of something else again, right? So this, then, is the result, or is the origin for what? Right, that's the origin of pressure, right? In that if my particles are always moving, eventually they run into things, right? And then, next principle says that there are no interactions between my particles. That's important because if there were interactions, like strong attractive forces, what would happen? Right, if there were strong attractive forces between any two particles, then when they collided with one another, because again, constant motion means that they inevitably run into each other, if there were strong attractive forces, then when particle A runs into particle B, they might stick together, and then we would have what? Right, condensation and or a chemical reaction, right? One or the other. But in this scenario, when we're talking about ideal gas behavior based on kinetic molecular theory, we say that there are no interactions between our gas particles, and every collision is elastic, meaning that the energy is 100% conserved, right, during a collision, which is why when a particle runs into the wall of its vessel, that energy is transferred to that wall, and the result is pressure, right, force over the area. Okay, there is lots of space between our particles. Your book has several figures on this, but another way to say number 3, right, is that the volume of an individual particle is negligible. Meaning that the size of the actual particle doesn't matter, right? We just got done talking about the relative sizes of different atoms. And so if we think about a helium atom versus a radon atom, helium significantly smaller than radon, but we say that when we are discussing the ideal gas, right, so how on average gases behave, we say that the particle size is negligible, right? So it doesn't matter that radon's a little bit bigger than helium because we're going to pretend that they're all the same size since they don't interact anyway, right? And the space between them is so ginormous that the particle size can't possibly be an issue, right? And the average kinetic energy is directly proportional to temperature in ding, 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 Kelvin, right? So don't forget, how do we convert between Kelvin? Right, plus 273.15, right, is how we get to Kelvin, right? So make sure you know that. And if you have forgotten how to convert between Celsius and Fahrenheit, go look that up also. Okay, next up. Pressure conversion. So your book goes through these. Your outline mentions these as ones to know. So note that they are all equal to each other, right? So I could say that 1 atmosphere is equal to 1,325 pascals, or 760 torr is equal to 14.7 psi, right? Likewise, these are all equal to each other and can be used in any way, right? So I could say 1 atm, 14.7 psi, right? Or I could say 14.7 psi is equal to 760 millimeters of mercury, right? If that's what I needed for a conversion factor. And do be mindful when we talk about this millimeters of mercury, right? That's like your book references the use of barometers, right? How we use to measure weather, right? Where we literally are talking millimeters, just like with a ruler, right? How tall a column of mercury is one of the ways that we measure atmospheric pressure, right? Which is why we could also talk about inches of mercury, right? But thankfully, you know how to convert between metric and inches, right? Right. Okay. Moving along, this section covers a few basic introductory gas laws, the first of which is Boyles Law, which says that P1V1 equals P2V2, right? It does have that alternative form that says pressure times volume is always equal to a constant, right? where what that says, right, and this is with the assumption that, right, assumption that moles and temperature are constant, right? Those pieces of information do not change. So what that says is if moles and temperature are constant, then pressure times volume is always the same number, right? So this could be 2, for example. But whatever it is, it's always the same number. So if I change one of these variables, I can predict what happens to the other one because their product must always equal the same number as long as this condition is met. Yes? All right. So P1, V1, that says that pressure and volume have what kind of a relationship? If one goes down, the other must, if one goes up, the other must go down so that the product always equals the same value. So it's inversely proportional, right? Which makes sense, right? Because if I squeeze something that has gas in it, right, in a flexible vessel, the volume will go down, right? Okay, so let's solve this problem real quick. So it says a snorkeler takes a syringe filled with 16 mils of air from the surface where the pressure is 1 atmosphere to an unknown depth. The volume of the air in the syringe at this depth is this, right? What is the pressure at this depth, right? So if we're looking at our information, right, we have a 16 mils, right? So that's a volume where the pressure is this. So this is my P1. So I have a V1, P1, I have a V2, and I'm looking for P2, right? So let's go ahead and solve, right? P1 is 1 atmosphere. This is 16 mils is equal to 7.5 mils times my P2. Now here, right, one of the neat things is, as long as we set it up neatly, all that has to happen is that our units have to match across the equal sign, right? So since this is 7.5 mils, when I divide by 7.5 mils, right, that unit cancels and I'm left with P2 is equal to however many atmospheres, yes? So this then is going to get me what my new P2 is. And then once I solve for my new P2, the rest of the question says if the pressure increases by 1 atmosphere for every 10 meters of depth, how deep is the snorkeler, right? So if we're at 2.1 atmospheres and the question says it increases by 1 atmosphere, so here at sea level, right, we have 1 atmosphere pressure. If I go down 10 meters, now I'm at 2 atmospheres. So that means this diver must be something just below 10 meters, right? Make sense? Okay, next up. Boyles Law is the relationship between volume and temperature, right? Which says that, and again, one of the other ways it's presented is that volume over temperature is equal to a constant, which then if we look at that relationship, if one of these variables goes up, the other one, right, must go up. If the division, right, has to always equal the same value, then they are directly proportional, right? Same principle though, right, in that whatever is not changing, whatever's not in my equation, so in this case, moles and pressure, must be constant, right? Or unchanging as we talk about the rest of the things changing. So gas in a cylinder with a movable piston has an initial volume of this, right? So here's our V1, and it's heated from 35, so that's our T1, to 155, and that's T2. What is the final volume in milliliters? So this is my V2. Now, what has to happen here? Right. If we think back to our principles of kinetic molecular theory, it is based on temperature in Kelvin, right? Because Kelvin is the only temperature scale that runs from 0 up, right? Which means that we can talk about proportionalities. If we're changing signs halfway through, the concept of being proportional doesn't apply. So we got to make sure that we always turn our temperatures into Kelvin. So we have V1 is 88.2 mils over my T1, which is 35 plus 273.15 Kelvin, is equal to V2 over 155 plus 273.15 Kelvin, yes? And then we would solve for V2. Yes, makes sense? All right, next up, combined gas law, where we take those two and we just put them together. Yes, in that if we look here, this is what? Right, that is Dalton's law, that's Boyles Law, and all we did was put it together, right? So here it says that a balloon has a volume of this, so this is V1 at a pressure of this, P1 at a temperature of this, T1, The balloon is submerged in water to a depth where the pressure is this. This is our P2, and the temperature is this. This is our T2. What is its volume? Question V2, right? So then we would just set up the equation, which says that we have 3.7 liters times 1.1 atmospheres over 30 plus 273.15 Kelvin is equal to, what am I looking for? V2, 4.7 atmospheres over 15 plus 273.15. All right, so note here, if one of these variables doesn't change, N is constant, right? So the amount of gas has to be constant. So if one of these variables doesn't change, right, so if volume were to stay the same, for example, right, then I would just be looking at the relationship between P over T, right? If temperature stayed the same, I'd just be looking at the relationship between P and V, right? That makes sense? Which means that actually, from here, we can actually extract one more gas law. If we look, right, we have P over T equals P over T if volume is constant, yes? That's actually Gay-Lussac's law, which is not in your book. It is in some books because depending on how you want to derive the combined gas law, right, one might be better than the other. But anyway, just things we should know. All right, next up. Avogadros Law. All right, so this one is the relationship between volume and moles, right? So V1 over N1 equals V2 over N2, right? And again, this means that P and T are constant. So, a chemical reaction occurring in a cylinder equipped with a movable piston produces 0.58 moles of a gaseous product. If it contains 0.11 moles before the reaction and had an initial volume of that, what was its volume after the reaction, right? So again, whichever one you call initial doesn't matter, or final doesn't matter, right? All that matters is your ones have to match, they have to be from the same scenario, and your twos have to match or be from the same scenario, right? So in this particular instance, we have 0.58 moles. What was its volume after the reaction? So I'm looking for V1, and I have 2.1 liters. And 0.11 moles, and I would solve for my V1. Yes? All right, fantastic. Make sure you have all this ready and prepped for next class period. So these would be our introductory gas laws, right? So obviously this doesn't reincorporate the concept of chemical reactions yet, but no worries, that is on the horizon. Make sure you pay attention to Power School for announcements for what you need to bring for that upcoming lab. All right, thanks for listening, be good, and I will see you soon. Bye.